Pluto, a dwarf planet with grand implications. Pluto, once considered a legitimate planet in our solar system, remains a dwarf planet that captivates and eludes explanation. Situated far from Earth, despite its previous classification, the most recent bold assertions by esteemed astrophysicists Neil deGrasse Tyson and Michio Kaku have stirred new interest in Pluto. They have suggested that Pluto's ice-covered surface could be on a trajectory toward a catastrophic collision with Neptune, prompting a flurry of questions about the plausibility and consequences of such an event. Could this scenario be an exaggerated theory, or is there a legitimate cause for concern? Let's explore the potential ramifications of a Pluto-Neptune collision. Initially classified as a planet, Pluto was reclassified as a dwarf planet due to its irregular orbit. This decision has kept it a subject of ongoing debate in astronomical circles. The latest studies by leading scientists suggest that Pluto's orbital path dangerously intersects with Neptune's, raising alarm about the possibility of a deadly impact. Given their proximity in their respective orbits, can a collision between Pluto and Neptune actually occur? And if so, what would the implications be? Pluto's journey around the Sun spans an intricate 248 years, which means that since its discovery in 1930, Pluto has yet to complete even one full orbit. However, the peculiar orbit of Pluto doesn't stop there. It follows an elliptical path that deviates significantly from the near-circular orbits of most other planets. To further complicate matters, Pluto's orbit is tilted 17 degrees to the ecliptic plane, making its trajectory much steeper compared to other planetary paths. An especially intriguing feature of Pluto's orbit is its intersection with Neptune's. For about 20 years during each of Pluto's prolonged orbits, it gets closer to the Sun than Neptune, a strange anomaly that contradicts the usual positions of these two planets in our solar system. This raises an important question: why haven't Pluto and Neptune collided yet? The answer lies in the powerful gravitational forces from other bodies in the solar system. After Pluto was discovered, astronomers quickly recognized the oddity of its orbit. Unlike the nearly flat orbits of the other planets, Pluto's steep angle and elliptical trajectory were starkly different. The complexity of its path became even more apparent as scientists realized Pluto's orbit crosses Neptune's. Despite these out-of-the-ordinary features, Pluto's orbit has remained surprisingly stable thanks to the gravitational effects from other celestial bodies. The three-body problem in celestial mechanics seeks to explain the actions and interactions of three bodies, such as Pluto, Neptune, and the Sun. Pluto's path through space can be erratic, as even slight changes in its initial circumstances can drastically alter its trajectory over long periods. However, simulations have demonstrated that Pluto's orbit has remained steady over extended time scales, indicating that its path is not as chaotic as it may initially seem. The significant gravitational pull from massive bodies like Jupiter plays a crucial role in stabilizing Pluto's orbit. For billions of years, these forces have been essential in maintaining the overall order of our solar system and preventing potential chaos. While Pluto's orbit demonstrates an intriguing balance of stability and chaos, it's important to recognize the inherent challenges in predicting the movement of celestial bodies, especially those with irregular orbits. Although numerical simulations can provide valuable insights, they also emphasize the unpredictable nature of space events, making long-term predictions uncertain. The concern raised by astrophysicists like Tyson and Kaku about a potential collision between Pluto and Neptune may seem far-fetched, but their warnings have caught the public's attention. If such a collision were to happen, the results could be disastrous for our solar system. The impact would release a great deal of energy, likely leading to Pluto's destruction due to its small size and icy composition. The resulting debris could pose a significant risk to nearby planets and their moons, including Earth. The effects of a Pluto-Neptune collision would not be limited to Pluto alone. For Neptune, the collision could significantly alter its atmosphere and orbit, depending on the nature of the event. Michio Kaku, a renowned theoretical physicist, provides a unique perspective on this topic. His extensive research into string theory and celestial mechanics suggests that understanding Pluto's orbit could yield valuable insights into the physics governing space exploration. By examining the gravitational interactions shaping Pluto's orbit, we can gain essential knowledge for future space missions. This knowledge could help scientists better prepare for potential space threats and aid in the exploration of distant regions of the solar system and beyond. The principles derived from Pluto's orbit also have broader implications for the study of other dwarf planets and trans-Neptunian objects. Pluto's complex orbit challenges our understanding of planetary motion, reminding us that space is far more dynamic and unpredictable than we often perceive. The connection between string theory and the mechanics of the universe highlights the importance of understanding how planets and other celestial bodies interact. In the event of a collision between Pluto and Neptune, it would be a landmark event in cosmology, offering a rare opportunity to explore string theory's predictions under extreme conditions. This collision would release vast amounts of energy and could potentially offer a glimpse into the behavior of elementary particles and forces at high energy levels, a major focus of string theory. Despite the fact that the direct impact on Earth would likely be minimal due to our distance from the outer solar system, the scientific implications would be profound. A collision of this kind would provide fresh opportunities to explore the universe's fundamental nature, particularly in areas relating to string theory and theoretical physics. The unusual orbit of Pluto continues to capture the imagination of both astronomers and space enthusiasts. The ongoing debate over its status as a dwarf planet has reinvigorated interest in its role within our solar system. The concerns raised by Tyson and Koku underscore the complex forces that govern the movements of celestial bodies, concentrating on the importance of understanding gravitational influences and orbital mechanics. These forces are vital for comprehending the solar system's dynamics. Pluto's steep and elliptical orbit defies conventional theories of planetary motion. Unlike the nearly circular paths followed by other nearby planets, Pluto's orbit intersects Neptune's at specific points during its long journey around the Sun. The gravitational forces exerted by planets like Neptune and others have played a significant role in stabilizing Pluto's orbit, ensuring it remains relatively constant over centuries. Despite this, predicting the future behavior of celestial bodies remains a complicated and unpredictable task. The possibility of a Pluto-Neptune collision serves as a reminder of the inherent uncertainties in planetary dynamics. Although such an event seems highly unlikely in the near future, the interactions caused by gravity between Pluto and Neptune illustrate the delicate balance that exists within our solar system. Understanding of celestial mechanics and the fragile equilibrium that sustains the harmony of our solar system. As we probe deeper into Pluto's mysteries, it becomes clear that this distant dwarf planet is far more than an icy remnant. It is a dynamic, evolving body that holds clues to the early solar system and the processes that continue to shape planetary bodies today. The implications of Pluto's unusual orbital behavior extend well beyond academic curiosity. They inform everything from space navigation to mission planning for spacecraft traversing the Kuiper Belt. The study of trans-Neptunian objects like Pluto provides a window into a region of space that, though distant, may hold answers to fundamental questions about the origins of water, organic material, and potentially even life in the solar system. Moreover, Pluto's interactions with Neptune demonstrate the incredible precision and complexity required to maintain orbital stability over cosmic timescales. These interactions act as a kind of cosmic choreography, where even slight gravitational nudges can drastically alter trajectories, possibly leading to ejections, collisions, or entirely new orbits. Understanding this intricate dance could be key in safeguarding Earth from future asteroid or comet threats and in designing stable orbits for satellites and space stations in deep space exploration. The discourse ignited by Tyson and Koku, though hypothetical, serves an essential purpose. It challenges our perception, pushes scientific inquiry forward, and reinforces the importance of continuous observation and modeling. In this light, Pluto stands not as a forgotten or demoted planet, but as a critical piece of the cosmic puzzle, mysterious, distant, yet essential to unlocking the secrets of our universe. As new missions are proposed and space technology advances, there is no doubt that Pluto will remain an object of fascination and study. Whether it continues to travel its solitary path or becomes a key to unlocking new theories of planetary science, its legacy is secured. The once ninth planet, though reclassified, continues to defy expectations and expand the boundaries of our astronomical knowledge. Understanding of planetary motion and the formation of the Kuiper Belt, a region beyond Neptune filled with small icy bodies, provides valuable clues about the gravitational interactions that may have shaped the early solar system. Understanding Pluto's orbit offers essential data for the future of space missions focused on exploring potentially habitable worlds outside of our solar system. Although the likelihood of a Pluto-Neptune collision remains extremely low, research into these celestial objects serves as a reminder of the ever-changing nature of the universe. As we continue to explore the far reaches of our solar system and beyond, the study of planetary orbits and celestial mechanics will remain central to our exploration efforts. Pluto's unique orbit offers valuable lessons about the complexities of planetary motion and the forces that shape celestial bodies over time. The continued exploration of Pluto's orbit and its interactions with Neptune serves as a reminder of the unpredictability of the universe. With every new finding and theoretical model, we expand our understanding of the cosmos and gain insights into the mysteries of distant worlds. The study of Pluto's orbit not only provides answers about this distant world but also helps us predict future trends in celestial behavior, contributing to a better understanding of the forces that govern our solar system and beyond. In conclusion, the possibility of a Pluto-Neptune collision, despite being highly unlikely, highlights the dynamic nature of the universe. The study of Pluto's orbit, its interactions with Neptune, and the gravitational forces at play offer valuable insights into celestial mechanics. As we continue to explore these distant bodies, we refine our models of planetary systems and enhance our ability to predict future cosmic events. There is no end to the field's discoveries, and as technology advances, so too will our ability to study and comprehend the vast, ever-changing cosmos. The exploration of Pluto's orbit and its role in the solar system will continue to shape our understanding of the universe for years to come. Pluto's orbital behavior, with its unique interactions with Neptune, has for a very long time fascinated and intrigued the scientific community. Despite its designation as a dwarf planet, Pluto continues to challenge our understanding of planetary dynamics. The fact that Pluto's orbit intersects Neptune's at various points without resulting in a collision highlights the complex nature of gravitational mechanics in our solar system. One of the most fascinating aspects of Pluto's orbit is its resonance with Neptune. This resonance, known as a 3:2 orbital resonance, means that for every 3 orbits Pluto completes around the Sun, Neptune completes 2. This carefully synchronized relationship ensures that the two bodies never come too close to one another, despite their crossing paths. In this resonance, Pluto and Neptune are essentially locked in a cosmic dance, where their orbits are set in such a way that they never collide. This unique gravitational relationship is an excellent example of the precision and balance that exists in celestial mechanics. The forces exerted by Neptune's gravity on Pluto and vice versa collaborate to keep a stable orbit for both. Without this resonance, a disruption in Pluto's orbit could have occurred, potentially leading to a collision or other significant perturbations in its trajectory. Understanding this interaction is crucial for astronomers, as it provides insight into how celestial bodies can maintain stability even when their paths seem chaotic at first glance. Moreover, the Kuiper Belt, a region beyond Neptune, is a treasure trove of icy bodies and dwarf planets. Pluto is the largest known object in this belt, and its orbit provides valuable information about the conditions that prevail in this distant part of the solar system. The Kuiper Belt objects, KBOs, and other trans-Neptunian objects, TNOs, are remnants from the early solar system, and their study allows us to peek into the conditions that existed during the formation of the solar system billions of years ago. Space agencies, guided by organizations like NASA, are now directing missions towards studying these far-off regions. NASA's New Horizons mission, which conducted a flyby of Pluto in 2015, provided us with unprecedented images and information about the surface and atmosphere of Pluto. The findings of this mission revealed frozen nitrogen plains, towering ice mountains, and a complex weather system, suggesting that Pluto is a geologically active world. It also showed the diversity of the dwarf planet's moons, providing clues about how moons form and evolve in the outer solar system. The New Horizons mission also illustrated the expanding capabilities of contemporary space exploration. Such missions not only expand our knowledge of distant celestial objects like Pluto, but they also pave the way for more ambitious explorations into the Kuiper Belt and beyond. The success of this mission has sparked renewed interest in exploring these far-flung regions and could inspire similar missions to other objects within the belt. Despite the apparent stability of Pluto's orbit, its tilted and eccentric trajectory also raises questions about the long-term dynamics of the solar system. The fact that Pluto's orbit is so different from the nearly circular orbits of the 8 major planets offers astronomers a fascinating puzzle. The inclined and elliptical nature of Pluto's orbit serves as a reminder that our solar system is not as orderly as it might seem at first glance. The chaotic behavior exhibited by Pluto's orbit could have profound implications for our understanding of planetary formation and evolution. These orbital peculiarities suggest that Pluto may have had a more tumultuous past than once believed. Some scientists theorize that gravitational interactions with other massive objects in the early solar system could have ejected Pluto into its current tilted and eccentric orbit. Others propose that such interactions may point to the possible existence of undiscovered planetary bodies, like the hypothetical Planet 9, that could still be influencing the orbits of Pluto and other Kuiper Belt objects. Such theories, while still under investigation, underscore the importance of studying outer solar system dynamics. Each new observation adds a layer of complexity to our models and challenges long-standing assumptions about planetary classification, orbital resonance, and the very architecture of our solar system. Beyond academic curiosity, these insights have practical applications. As we plan future missions to the outer reaches of the solar system, and even consider sending probes beyond the heliosphere, understanding the gravitational relationships and orbital mechanics at play becomes essential for trajectory planning, mission safety, and scientific return. In addition, Pluto's geological diversity, atmospheric activity, and its interaction with solar wind raise questions about the potential habitability of distant, icy bodies. Though Pluto itself is far too cold and lacks the necessary conditions for life as we know it, the lessons learned there may help guide our search for life on exoplanets orbiting distant stars, particularly those in similarly extreme environments. As we refine our instruments and launch increasingly advanced telescopes and spacecraft, we are poised to uncover even more about Pluto and its surroundings. Future missions may involve orbiters capable of sustained study, landers that could analyze surface composition up close, or even deep space telescopes trained on the distant shadows of KBOs. In many ways, Pluto serves as a frontier, not only of distance, but of knowledge. Its study connects disciplines: astronomy, planetary science, astrophysics, and even cosmology. It reminds us that exploration doesn't always yield clear answers. Rather, it opens up new and sometimes more profound questions. Ultimately, Pluto's orbit, its resonance with Neptune, and its place in the Kuiper belt are more than curiosities, they are windows into the past and guides for the future. As we continue to push the boundaries of our understanding, Pluto will remain a symbol of how even the most distant and unlikely worlds can reshape our view of the cosmos.